Hi, my name is Charles Kaplan. I'm a professor at the State University of New York at Old Westbury, and this is the fourth video, probably of 5 videos on the chain rule. So let's start off. We have a function here, f of x is equal to x over the square root of x squared plus 1. Let's differentiate this first. What we need to do is we need to rewrite this, getting rid of the square root symbol, but also in the same time I'm going to rewrite. I'll do it in 2 steps. I'll burn an extra step. So f of x is equal to x over x squared plus 1 to the 1/2, and this is where I'm talking about burning the extra step. I could have done this on a test or homework or whatever. I would have done this if I were a student, I guess. I would have done this all in one step, but here's what we're doing. F of x is equal to x times x squared plus 1 to the negative 1/2. So we turned it into a product rule problem instead of a quotient rule problem by using the negative exponent. Okay, so now let's just I'll review the product rule quickly for you here. Let's see. So let's write this out. Product rule. And we have 2 functions, f of x times g of x. And to differentiate this, we're going to take the derivative of the first function, f prime x, and we're going to multiply it by the second function, g of x, and then we're going to add the derivative of the second function, g prime x, times the first function, f of x. So there you have it. That's the product rule. Okay, so let's get back to our problem, which is to differentiate this mumsa. Okay, so f prime x is equal to, well, the derivative of x is 1 times this, the second function, x squared plus 1 to the negative 1/2. And then to that, we're going to add the derivative of this second function times the first. So we're going to be multiplying it by x. We bring out the negative 1/2. I'm running out of page to the right. So let's go down here. Times x squared plus 1. Now, negative 1/2 minus 1 is negative 1/2 minus 2/2, which is minus 3/2. And then we're going to multiply this by the derivative of the inside function here, which is 2x. Right? The derivative of x squared plus 1 is 2x. Okay. So now, as I've mentioned before, it's the algebra that makes these tough, not the calculus. The calculus is easy. The calculus is over now. Okay, so x squared plus 1 to the negative 1/2, well, that's the square root of x squared plus 1. Only we put it in the denominator. And then x times 1/2 is negative x over 2 times 2x. I really don't want to burn an extra step here. I've done it enough in these videos. This is just simple algebra. Well, 2x times x is 2x squared times negative 1/2. The 2's go out, and we're left with minus x squared times x squared plus 1 to the negative 3/2. Well, this negative 3/2 says put this guy here, this term, x squared plus 1, in the denominator, so that's what we're going to do now. So f prime x is equal to 1 over the square root of x squared plus 1 minus x squared plus 1 to the 3/2. That's a pretty lousy looking 3, isn't it? To the 3/2, and we have x squared in the numerator. So, okay, so now what we need to do is we need to, this is the derivative, but it's in an unacceptable form. We need to combine terms. We need to get it into one fraction. We need a common denominator. That common denominator is right here, x squared plus 1 to the 3 halves, a very bold 3 halves there. Well, this is x squared plus 1 to the half, right, the square root? So a half plus 2 halves being 1, is 3 halves. So we're going to multiply this left term on the left side, by x squared plus 1. You'll see what I'm talking about here in a moment. Let me move this up so that you can keep this in the frame. There we go. So, okay, so I'm going to take f prime x, the derivative is, let's see, x squared plus 1 over 1. We're going to multiply this by x squared plus 1 over x squared plus 1. Because this term here, let me actually, let me do this, minus x squared plus 1 to the 3 halves, with x squared in the numerator there. Let me just rewrite this and show you what's going on. This is x squared plus 1 to the 1 half times x squared plus 1 over x squared plus 1 squared plus 1 to the 3 halves here. So when I take x squared plus 1 to the 1 half and I multiply it by x squared plus 1 to the 2 halves, or 1, right? This is just x squared plus 1. We're going to wind up with, let me get rid of this now. We're going to wind up with x squared plus 1 in the numerator and x squared plus 1 to the 3 halves in the denominator. And here, okay. So now we can combine terms in the numerator and we can put it all over the same denominator. So let's do that. F prime x is equal to, well, x squared plus 1 minus x squared. You should be able to see what's going to happen in a moment. Over x squared plus 1 to the 3 halves. Obviously this term and this term drop out, and we're left with f prime x is equal to x squared plus 1 to the 3 halves in the denominator and 1 in the numerator. So there's the derivative. We started off with this guy. We started off with this function. We rewrote it and we worked it as a product rule problem, and we wound up with this fellow right here as the first derivative. So there you have that one. We have time here. So, you know, I just realized a few minutes ago that I really haven't been working any, not really, I haven't worked any trig functions, chain rule problems with trig functions. So let's chain rule trig functions. Okay, and let's just write these out. So we have sine of theta. If we want the, the derivative of that, well, the derivative of sine is cosine theta. The derivative of cosine is negative sine. The derivative of tangent theta is secant squared theta. The derivative of secant theta is secant theta tangent theta. Ooh, I'm running out of page. Am I going to get the last two in here? And the derivative of cosecant theta is negative cosecant theta times cotangent theta. And it looks like I will. But I need every bit of this paper. The derivative of cotangent theta is negative cosecant squared theta. So, okay, so there's the derivatives of our 6 trig functions. We're not doing the inverse trig functions now, but here's these. And let's make up some problems. How about that? So these are all going to be chain rule problems, but with trig functions. Okay, how's that sound? Pretty good? So how about y is equal to, how about cosine 3x? Okay? Now, this is a chain rule problem, so we're going to take the derivative of cosine is negative sine. We're going to repeat this, 3x, and we're going to differentiate the 3x and multiply by that, which is 3. So y prime is negative 3 sine 3x. You can put the parentheses in or not put the parentheses in, whatever you prefer. So there's one trig function under our belt. We'll do 1 or 2 more here real quick, and then I'll put some more trig functions on the next video. How about this? Y is equal to, actually I shouldn't do that, I'll probably do something wrong. Y is equal to, how about sine pi x? Okay? So y prime, the derivative of sine is cosine. So it's cosine, and we'll repeat that, pi x. Actually, I prefer to put parentheses around these things. And then the derivative of pi x is just pi. So the derivative here is pi times cosine pi x. So there's that one. That's a relatively easy problem, and it's a chain rule problem. So let's do another. I think we have time for another one. Chain rule trig. How about y equals 3 times the tangent of 4x? Well, we could actually do this as a product rule first. So we could do 3 times the derivative of 3 times the tangent of 4x, but that derivative of 3 is 0. So it's 0 times this, which is 0, plus, and then the derivative of this thing. So we can forget about that. So the derivative of tangent is secant squared. So we're going to take 3 secant squared 4x, and then we're going to differentiate the 4x, which is 4. So y prime is 12 secant squared 4x. And that's it. This is Charles Kaplan. I'm a professor at the State University of New York at Old Westbury. I hope you found this video helpful on the chain rule. I have one more video I'm going to be making on the chain rule. This is the 4th one. So I hope you all enjoyed it. Hope you found it productive and helpful. Bye-bye.